Okay, ladies and gentlemen, we are ready to get going now, and pleasure to have you all here this evening. Thank you for turning up. Well, I say this evening, the wonderful world of Zooming and the internet as is. Of course, it could be morning somewhere, but so thank you for turning up in whatever respective time zone you may be on. My name is James Lyne. I'm the SANS Chief Technology Officer, and an absolute pleasure to be here today for this keynote session where I have planned a litany of fun topics and demonstrations to walk through with you. It's going to be a really demo-packed session today, so much so that I'm actually even just starting with a screen share. I do have 2 slides at the end, but the rest of this session is going to be very, very hands-on and hopefully a lot of fun. Now, before we kind of dive into the agenda for today, I want to point to just a couple of the standard moderation features. I know after a year of Zooming, we're all rather used to these features, but there is the Q&A button that you can press at any time to drop a question. As I'm walking through the demonstration, if you have a query about what I've done, the tool I'm using, why I've done it that way, or just, anything on life in the universe, frankly, that you feel like chatting about, then feel free to drop it into the Q&A section, and I'll stop intermittently and try and make sure that I pick those up. We also have a couple of moderators helping us today. Huge thanks for the technical assist in getting this session up and running. And I'll have that on my system over here, so you can ping me anytime if I've lost my internet connection or something goes horribly, horribly wrong. So again, a big welcome from me to this keynote session at SANS 21. I know we have lots of classes underway, lots of students taking kind of fascinating courses, learning about everything from forensics through to offensive disciplines, defensive, the whole gamut of cybersecurity topics. But today, I want to give you an interesting talk about the power of foundational topics, basic concepts in computing. But I want for each of you here, many of whom will be more technical cybersecurity practitioners, take you through a little story, a little journey, in fact, from some of the kind of foundational skills many of us learned many years ago with computers, through to some pretty advanced demonstrations, including a little bit of bug hunting, a little bit of exploitation. So whilst this might sound foundational, we're actually going to apply those foundations to some really pretty advanced material. And I hope through that, I can show you the value of some of what sometimes seems like the more academic fundamentals and foundations to enabling us to take on some really pretty advanced concepts in modern cybersecurity. Now, this is going to be a bit of a journey. We have a lengthy session here where we could take as much as 2 hours. And based on the number of questions, my level of excitement, the amount of caffeine that lands on my desk during this talk, we'll see how much we can fit in. But if you all get horribly bored and leave, then, well, who are we kidding? I'll probably just complete the demos anyway because they're fun for me. But we'll take this session and a real gentle pace through this to make sure that everyone here kind of understands what I'm working on. So first and foremost, let me open up my agenda text file here on my screen share. I thought it was only fitting in a talk about the foundations, programming, encoding, hardware architecture, and shell hacks and tools like that, that my agenda text file should be a set of ASCII values represented in Vi. Of course, my favorite text editor, nice and memory efficient on my Mac here. No one uses Emacs. That wouldn't leave any space at all to run any other programs. And so I'm just going to quickly run this through a little Vi escape sequence here to reverse it to my actual text to get going. I know that was a cheesy start, but it gave me an opportunity to make jokes about Emacs. So, I mean, that really only seemed fair to me. So the importance of foundations and 3 live demonstrations to step through. I'm going to take a look at hunting for some bugs and finding things that might be exploitable. We're going to take a look at breaking bad code, code that sometimes developers write that's well-intending, and how that can lead to vulnerabilities. And finally, we're going to take a look at a pretty tough CTF challenge here and use some foundational scripting skills rather than a high-end security tool to break this stuff. We'll step through each of these one by one, leading up to some pretty challenging stuff. Now I see that someone's leading the charge in the Q&A with what is the answer to the life, the universe, and everything. Of course, that is an absolute classic, 42. We already know that one, but that is, of course, also expressible in hexadecimal values, which we know hex is really the encoding scheme of the universe, or the base of the universe. So translate as you will. So why this topic and why these demos? I've been working on a really interesting project over the last year. And before we get into the super technical stuff, I want to tell you a little bit about it and why I've been doing it. The project is called SANS Foundations, and it's all about teaching newcomers to the industry, people pivoting into cybersecurity, or people that have been in cybersecurity for a while who need a refresh, the foundations of computers, technology, networking, and programming. It's actually very little to do with cybersecurity at all. It covers things like how computers operate. We build a computer. We talk about what a CPU is, what memory is, how file systems function, how packets are transmitted on the network. Now, these are all things that many of us on this session here will have learned over the years and applied in cybersecurity. Of course, these days there are more foundations than when we got started. Things like the cloud, like the importance of understanding services in AWS and Azure and Google Cloud and whichever cloud comes next. So the foundational topics on which most modern kind of technology runs are expanding. But unfortunately, there is a phenomena that I've observed that makes it really tough for people to grasp some of the kind of more advanced cybersecurity topics where their foundational understanding is weak. And I'd liken it a little bit to doctors and surgeons and the study of medicine. You, as you're going into surgery, and I'm not wishing that upon you, but at some point in your life, if you are, will be going in with a surgeon who's spent years practicing, being through examinations, proving their skills to handle a life and limb scenario. But they also studied anatomy, and that anatomy study was really important to all of their comprehension of the topics that followed. Yes, they might have got in and used a knife on some things, but of course that anatomy understanding was the building blocks of all their further study. And the reason I've been so passionate about this Foundations project is I think these topics do the same for lots of our understanding in cybersecurity, as you'll see as we go through these demonstrations. Now, depending on how technical you are, how long you've been in this industry, which course you might be taking, you may find some of this material easier or harder. But let me draw a little distinction between technology today and technology when I got started. And hopefully I'll get some hand raises or some chat, thumbs up from some people in Zoom here on this little associative story. When I started using computers, if you wanted to get the latest video game running, you'd be into Config.sys and Autoexec.bat, enabling high mem to get Commander Keen to run appropriately. But a little later, there was wrestling with drivers. Remember when drivers were really hard to install, and things just didn't work like today, where you had to have that exact model of Sound Blaster, and if it was off by one revision, it wouldn't play properly, or that brief period of physics cards and so on and so on. Technology was harder. It was less intuitive. Some of you will remember the pain of copying out code from a magazine line by line, making about 5,000 errors synatically so you could get the latest game to run, be that a basic color version of Pong or whatever it might be. I'm hoping I'm invoking some fond memories for some of you here, and maybe a few nightmares as well, given how hard some of this stuff was. But whilst we were doing those things, we were learning a lot about the foundations of computers, how they function, how memory is addressed, the things that could go wrong, and troubleshooting. We learned a lot about syntax and scripting, that as concepts, even if we weren't true masters of that syntax, really helped all of the study that followed when it came to these more advanced topics. And one of the challenges today is you pick up your latest shiny computer, you pick up your M1 Mac running in a completely new, instruction set and architecture compared to what you used to run, and it basically works. I mean, most of the time it doesn't crash. Software's functional. There's very little configuration hacking to get the majority of use cases. So people can be amazing users of technology without getting into the hot water that helped a lot of us to learn skills that have been foundational to our careers. And that trend has obviously continued. And that presents a worry for me for the future in making sure that people understand how technology actually works, so that in turn they can pick up all these skills that are really quite fascinating and fun. It's a bit like the discussion many of you have probably had over the years of why learn programming as a cybersecurity professional. Now, I'm not saying that in order to be successful, you must be able to code. There are lots of people probably on this Zoom call right now who aren't programmers and who are very successful in cybersecurity. I'm not saying you have to be a staff developer and get your expertise up to the level where you can, program and build amazing tools and, go and debug. But a little bit of comprehension of how computers take code and turn it into things that are executed is actually incredibly valuable as a learning accelerator when it comes to the more advanced cybersecurity disciplines. So I've said a lot about this, and hopefully it's a little hard in the world of Zoom. If you stood up in a room, you get a litany of people in front of you. You can see faces, you can see people nodding or kind of hitting their forehead at the memories of trying to get Commander Keen running or whatever your favorite game was. But hopefully you're all with me. And with a lot said about the importance of foundations, I want to dive into some demonstrations here of some more advanced material and talk about how the foundations help understand it. Now, remember, you're more than welcome to raise questions as we go. If you get stuck, if you're confused, we've got time to work through this. And if you don't follow literally everything, that's okay, because for foundational talk, this is going to be mightily advanced, which is going to make it really, really good fun, I hope, on this, this fine Tuesday evening/morning, depending on where you are in the globe. So first and foremost, I want to dive into an example that's actually covered in one of my favorite SANS courses, which is the SEC 660 course, Advanced Penetration Testing and Exploit Writing class. And I love this one because over the years, I've seen lots of students write their first exploit, break into a program and trigger it to run code that it shouldn't. And the smile on their faces as they get that to work and really get it for the first time. Now, this little example is going to cover a bit of bug hunting. Now, some of you here may have done this. Others will have watched as cyber criminals and others successfully managed to get code running on computers after you opened a file or visited a web page. But of course, the precursor to any of that is being able to find bugs, create crashes in computers that can be used in interesting ways, things that can be turned into vulnerabilities and exploited to enable us in turn to create that effect. And of course, as cybersecurity practitioners, we want to find them so we can close them off before people with less altruistic and ethical intents use them. So let's start with a little bit of, a little bit of a demonstration of a bit of bug hunting. And I can see the questions building up as well now, some serious, some less so, but okay. So what I've got here is a program called TCPIC. Now, this is an oldie but a goodie bug. And the reason I picked it is it's a little easier to follow because it's older, and because, of course, it's safer to pick an older bug versus a newer one. Also, generally, when you're trying to learn these more advanced topics, there's a connection here to foundations too. Going back to the old stuff and then working forwards is a wonderful way to do that. You know, if you were trying to become really good at math, you wouldn't start with, you know, algebra or quantum electrodynamics. I appreciate I didn't really put those in the same playing field there. That was a bit off skew. You'd start with simple arithmetic and multiplication before you went after axiomatic logic and calculus. Same thing here. You start with the basics, you work through the older stuff. The same fundamental principles apply, the foundations, and then they grow more advanced in time. So let me start by extracting a copy of this program, TCPIC. And this is the version that is listed on the author's webpage, 0.21. And it has this bug in it that we're going to be finding. Now, I know where the bug is, and I know what causes it, but we're going to work through a bit of the process of finding it. And by doing that, we're going to have a little look at some bug hunting techniques using some fun tools here. Now, the first problem that we're going to have is also a bit of a foundational problem, which is actually building this software. So we're going to run the configure script, which tries to set up the build environment for this, this particular process so we can build it. Configure script runs. Notice here, I have a lovely shell prompt. This is a very nicely styled prompt. I think you'll agree, much better than the standard. This is ZSH running with antigen and the power level 10K prompt. I've customized it a little bit so that it shows me the execution time on commands, the time, the exit status, whether it returns successfully, and got it customized here with a nice highlighted copy of the directory path. This is one of my preferred shell setups. Ironically, it's quite heavy. It takes up a lot of memory for someone who was being mean about Emacs earlier. But it is rather pretty here. Okay, so let's do a make on this to build it. It runs through, there's lots of warnings, and it breaks. We don't get a program. Well, the problem here is this particular program was built to run on an earlier version of Linux, and some things have changed since then. Thankfully, however, there are a set of patches that are available to fix this problem. And I found them by just searching for TCPIC, 0.21, Ubuntu or Debian, and I found the kind of patch maintainer's site where the package was listed and just downloaded them. So foundational skill, one could argue, is the ability to use a search engine rather effectively. Actually, that's not a foundational skill. That's a superpower, frankly. You could solve just about anything with a good search engine. So let me show you one of these patch files just quickly. They are under here, Debian patches. Here are a series of the patch files. So for example, there's fix build with gcc5.patch. And these are patches that we want to apply to this program to enable us to build it. So let's just open up fix build with gcc5. What you can see is it's a particular format of text where it shows what it's adding in and what it's removing. It's a patch file, right? It's changing the contents of the code. Well, again, here you might benefit from a few programming skills in that with a patch file like this, you could start to read some of the syntax and understand what's happening. But that comes later. We're not gonna go and dissect all of this to start. Let's go back to our TCPIC directory. and we're going to use the patch command to apply these patches. So they're going to be applied at this directory level, and I'm going to go to the Debian directory to patches, and I'm going to pick a select set of patches here. And the reason I'm going to do that is if I apply all the patches, I'm going to patch the security vulnerability that I want to take advantage of, which would make the demo really boring about 23 minutes from now. So we're going to pick our patches a little bit more carefully here. Okay, in a couple of minutes, I will pause and have a little look at some questions here. Keep them coming. If I don't see questions turning up or rampant anger and thumbs down in the chat, I'm assuming you're having as much fun as me, and I'm just going to keep talking and going through the demo. So be warned. So let's have a look at the fix patches. We're going to do fix build with GCC 5. That's one of them. So it's patched the files. We will also fix the double free. And in theory, that should allow us now to build the program. And it did. Notice here, there's no error at the end. There's still plenty of warnings. And that's because this software is doing some iffy things. Look, these are bugs here using setuid. That's a pretty important function that sets the user ID of the running program. That's serious functionality, and it's ignoring a result here that may or may not actually be useful, exploitable, or otherwise. But it's concerning. And you might think, what an awful piece of software. Who would write something like this? Well, actually, this is just software. This is just what it tends to look like. Developers are, busy people. They're working on large projects. They have different coding standards. They're under, challenging timelines to get things done. So it's easy for code not to be perfect. And even when you try for it to be and resolve these types of issues, there are more subtle bugs that can appear. So let's check that our program works by going to the source directory here and running the tcpic. Cool. That works. I mean, it runs and tells me I don't have permission. It didn't crash. So it looks like I have got a viable copy of this program building on my my computer now, just like I'd get from the package version if I were to use something like apt-get. But the reason I wanted to build this with source code was to go bug hunting. And we're going to be using a tool here called American Fuzzy Lop, AFL. If you Google AFL or American Fuzzy Lop, you'll find the top hit is the author's webpage. It tells you all about this tool, including a wonderful write-up of how they optimize the tool and the test cases to be effective here. Again, a great application of foundational knowledge, because you can read through it and understand how they built the algorithms to solve these problems effectively. So foundational knowledge makes that paper intelligible. The second hit is a Wikipedia reference to the American Fuzzy Lop, which apparently is a rather lovely rabbit, has very long ears, and it's fluffy. I guess that's the fuzzy reference. So both good articles, rather different, one more useful to cybersecurity than the other, but I'd recommend them both. So let's set up American Fuzzy Lop here so that I can show you how it can go and basically do a bunch of tests with this program to see if it can create some crashes that we can explore. So let me go back here to my tcpic directory, and I'm going to make a couple of directories here. I'm going to make one called in, and I'm going to make one called out. And you don't need to point out I could have done that in one line. I just wasn't thinking ahead enough. I did that on purpose to make sure you were paying attention, of course. Okay, so these directories are going to be used to generate files we feed in and files that the program generates and puts out the other side. Okay. Now, AFL is pretty magical stuff. without getting too detailed, the way it works is it takes a program, and it can work with source code or it can work with pre-built binaries. It's a lot quicker with source code. And it can put in these little points into the source code that reports where the program's up to in execution. They're instrumentation markers. So again, using our foundational knowledge, we know that a program loaded from a file like an ELF or a pconf on Windows is loaded into memory, it's mapped. We jump to the place where execution starts. And this tool inserts a bunch of key points into those programs, which says, hey, I'm up to here. This is where I am in execution. Well, that's useful because when we're trying to find bugs, our goal is to do two things at a high level. One, to touch as much of the program as possible. You can't find bugs in code you don't touch. The second objective is then to find ways to supply data to that code that in turn will cause the program to crash. So those are our two objectives. Well, this program is able to instrument our path through a binary. So it can feed some data in, see where we get up to in the program and go, oh, we only got through 2% of the program. That's not very much at all, is it? And then it can try changing the data. It could change it 1 bit, 1 byte. It could randomize the data, it could mutate through it on a numeric basis, all kinds of rules. And it feeds the next frame of data in. And the program this time gets to 2.1%. Oh, it's an improvement. Then it can do this thousands and thousands and thousands of times per second, or hundreds, depending on your quality of hardware. And it can chart a path to touch more and more of the functionality of the program. Well, we like this, right? It's a kind of algorithmic or machine learning approach to coverage of the program and finding flaws. We like this because doing it manually is really time consuming and annoying. It's really hard to write files that cover the functionality of a program comprehensively. But this is going to do all of the work for us. And I love that because I can set it up and I can go and have a pizza, come back and hopefully have some good results. So lots to love here. Now, of course, once we kind of are touching that code, we also hope it creates some conditions that the developer didn't anticipate, and it creates crashes. Some nods here to foundational knowledge before we actually do this. It's going to run this program hundreds or thousands of times per second. Well, if it's going to do that, there is a small problem. I'm running an SSD on my system here, and each time I run this program, I'm going to be making a file, and I'm going to run it thousands of times. Some of you are probably going already. SSDs, of course, slowly degrade with more and more writes. So large numbers of writes and executing this program is, well, it's going to wear out my disk progressively. So one of the things we could do is to make a RAM disk. Again, great foundational knowledge. This will also speed up the process significantly. So let's do that. Let's make a RAM disk. We're going to make it under temp/RAM disk. That's where our mount point is going to be. So mount-t, we'll find out now if I've got temp.fs installed or whether it's going to be a problem. Only 256 megs, well-ish. Temp.fs, temp RAM disk. Oh, that's fine. Okay, doesn't like temp.fs. Let's try RAM.fs. There we go. It likes RAM.fs, but not temp.fs. Pro tip, basically the same. So one or two things will be happening here. You'll either be going, oh, that makes total sense, or I have no idea why the Starship Enterprise is attacking the Romulans in that command line. If you're in the second category, what we've done is we've created an area in RAM, our volatile memory, and we've created a file system in that RAM rather than on the disk at temp RAM disk. So we can go to temp RAM disk. We could do ls touch file.txt. No. Haven't set permissions very aptly. And I can make files and use it like a normal file system. But pros and cons, it's in RAM, so it's fast. Other pros, it's not going to bury my poor SSD as I'm working here. And super, super pro, it's also at very high speed here. I'm going to produce results that I can quickly copy to my system for further analysis. Major con, it's a RAM disk. RAM is volatile, as we know from our foundational knowledge. If your computer crashes, if you reboot it without copying the results, what happens to all the data? Disappears, unless you are really fast and executing some super ninja attack like the Kingston attack, where you're ripping the RAM out and chilling it and cloning it. It's not going to go well. Some of our forensics brethren here might be able to recover that data, but better to remember to just copy it out first. All right, well, let me go back to the downloads directory here. I'm actually going to be lazy and use the in and out directory that I already created here. Because I'm inside a virtual machine, the effect of my SSD is minimized here, but we could copy it over to that RAM disk if we wanted to. Now, I told you a little bit about how this generates files by trying to iteratively find ways through the program to use more functionality. I'll give you a mental picture here, and quite an interesting property. Let's say you have a program that reads JPEGs. It reads JPEG headers. It knows how to render the colors, how to do the metadata. I mean, JPEGs are complicated files. What would be the best type of file to touch the maximum amount of functionality possible? Would it be a file with 1,000 A's in it? Would it be a file with random data in it? Or would it be a file that contains valid JPEG data? Well, pro tip, it's the last one, isn't it? Because of course that triggers the maximal amount of functionality. It has to do the most work when the data is valid versus exiting quickly. It might not be the most valid to crash it, but it's the most valid in order to trigger functionality. Well, this leads to a really weird property. And the author of this tool has some wonderful examples of this on their website that are worth looking at. If you go and feed into a program that makes audio files, that reads audio files with AFL, it'll, let's say, start with the letter A, 1 byte of data, and it will work through thousands and thousands and thousands of iterations. And it will learn through ML how to create a valid audio file. And that valid audio file, in turn, will probably be really quite creepy. It'll reverse engineer the audio file format. All right. So sorry, I had background noise there. So that's in of itself interesting, a fun way to go and actually create audio files, or JPEGs, some of which might be the stuff of nightmares. So let's replicate this process here with TCP and use network packet capture files. Right? TCP reads PCAPs. So we're going to start with a file that looks reasonable and see if it can iterate from it. Again, from a foundational understanding and a computer science perspective, people can be tempted to provide lots and lots of input data, but we want to provide something simple it can iterate from, rather than a huge amount of data that it has to work with reductively. Usually, additive iterations are more efficient than reductive iterations. So let's do this. Let's go to the in directory. And I'm going to use TCP dump a network packet capture tool, no name resolution, capture the whole packets, write them to a file called james.pcap, and I'm going to capture port 53 DNS. I'm going to do that because it's going to make it easy to just quickly create a packet with a connection to a root DNS server or something like that. So I'm going to put that off in the background. There we go. I'm going to go netcat 8888 port 53. I'm going to terminate that, and then I'm going to kill TCP dump. Okay. So what we've done here is started TCP dump, listen for port 53, used netcat to connect on port 53 with TCP, and terminated the connection. Again, foundational knowledge of what's going on here. We understand that by initiating a TCP connection, there's probably been a three-way handshake to 8.8.8.8. We haven't actually done a DNS query. We've just opened a really simple packet connection. Let's have a look in our directory. We have a james.pcap, and we can also see it's got a size of 1018. So there's data in there. If we want, we could open it up. Oh, it's a fascinating file. We could put it into kind of hex edit mode with vi. And I mean, it kind of looks like packets, right? There's the beginning of a packet there. It's got some kind of TCP headers on it as well. Some of our network forensics folks will be noticing the plain text data in here, but the IP level data with things like a 45, 4 being the IP version, 5 multiplied by 4 being the IP header size. Again, with foundational knowledge, this becomes easier to spot which fields do what from a networking perspective. But of course, we're very lucky these days. We have tools to help us read these things, because this is a lot harder than it needs to be. If we want, we could do a TCP dump. We could read james.pcap, and we can see we have some back and forth traffic here between my IP address, ephemeral port number, and 888.53. Not a lot of data. There's a DNS query for Ubuntu and my TCP connection. So this is a pretty boring file, and we're going to use it for the basis of trying to get this program to crash. To show it doesn't to start, let's do a tcpic /source tcpic -r. There we go. Those are just some arguments for tcpic, the tool. They're not super relevant. So you can see it can read the packet file just fine. Again, you can validate the functionality with your foundational understanding here. All right. I'm hoping you're having fun here. Let me have a quick look at the questions screen, and then I'm going to double back over, and then we're going to use a program to crash this and see if we can understand why it breaks. All right. Advanced techniques are basic techniques mastered. We are tracking. Yes, Paul, I completely agree. When you have a strong foundational skill set, you continue to master them. They're the building blocks of more advanced skills. I love that way of describing it. Very elegant. Chandra, if I blatantly plug foundations, will I get a lifetime access to CyberStar? See how excited I got there? I threw my computer on the floor. Well, obviously, I mean, that goes without saying. And hopefully from foundations, you're following some of what I'm doing here now as well. So we'll switch over to you for lecture near the end. Why ZSH? I like it. I really like antigen ZSH. Wow, lost the ability to talk at this time of night. ZSH and the power level 10K for how customizable it is. I like the historical command highlighting, makes it very easy to edit script statements, as we'll see shortly when we're working through some of the stuff. It's just more feature rich than the average shell. I don't depend on it. I'm often tied to bash or kind of more simple shell scripts. but I find it accelerates a lot of the things I do day to day. And I love the plugins, like enabling me to CD to a directory with GitHub commits and see what's in the master branch, what's not, and what's yet to be committed with color syntax highlighting. So it's just the functionality. And if you haven't checked it out, go try it on a test system, play with it, and have a look at the plugins, the syntax completing for Docker, for AWS, all the different tools. It's pretty funky stuff. Okay, Abdul, I'm going to answer your question at the end once I've been through a bit more of this, because it's a bit longer. And Michael's question here. So why does this process look like analyzing a more complex program that takes more types of input and data, or what does this process look like? Actually, very similar. This particular tool can deal with lots of different inputs and types of functionality, but it's good at binary files. So this program might be simpler, but it works just as well for really complex stuff. Sometimes you have to do a little work, Michael, to battle the inputs. I actually found a bunch of bugs in PHP a few years back with exactly this tool and setup. I ran it for a month, going over the surface area of the code, found numerous interesting bugs that were reported and fixed. And PHP is very complex inputs. Not only does it have complex inputs, but it has complex semantics and syntax, which can make the bugs really quite subtle. And this approach that I'm demoing here was actually really effective with that too. If you want to see how far that goes, Michael, a little swing via the author's webpage, and you can see their Bugorama trophy list. You can see they found bugs in, Internet Explorer, Chrome, libjpeg, SSH, very complex and realistic programs. And even if not using exactly this implementation, the technique being described is one that's very portable to lots of other use cases. So very similar, though more time and patience may be required than a quick webcast here. But this is certainly not a contrived setup compared to the real world. So hope that helps, Michael. All right, I'm going to dive back to my demo, but keep the questions coming. I will periodically swing in here and pick them up as I'm going, particularly if you're getting lost and it's not making sense, let me know. Otherwise, I can see the number of participants is not plummeting. So you either have nothing better to do or you're enjoying this as much as me. And I'll take either. Either's okay. All right. So let's go over to AFL here and build this program in a way that it's instrumented so that we can find some bugs. Now we're going to be doing this the source code assisted way. That means we are going to be inserting those instrumentation points into the program so we can execute it really quickly. We're going to be doing that using the AFL GCC wrapper method. And again, with foundational understanding of a bit of programming and compilers, it's a bit easier to see how this is happening, but we're going to talk through it. Now, I've still got my patches applied, but I'm going to just do a little make clean. I still have my in directory and my out directory. I've got rid of, the built version of tcpic, so we can make a new one. So I'm going to run configure, and I'm going to say compiler equals, that's wonderfully unfortunate Zoom bar position. Compiler equals AFL-GCC, which is the GCC compiler wrapped with AFL to insert these instructions. Do the same for CXX, AFL-G++. And lastly, but not least, disable shared. We don't really want lots of shared libraries here when we're running this, because each time loading them is going to take time when we could be running quicker. So we want this all to be in one place, and it might cause changes in the results, program invocation to program invocation. So we're going to say no shared libraries here. Please build it all in for us. So let's run this. By the way, I've just realized we're basically doing about 2 hours of continuous live demo. What could possibly go wrong? Oh, this is quite terrifying. So let's do a make. Okay, so look at this. This is, I know it looks like a wall of text, but some pretty cool stuff happening here. Look at this. Instrumented 6 locations, 64-bit, non-hardened, instrumented 15 locations, instrumented 12 locations, etc., etc. And the warnings are still here too. So AFL's GCC has wrapped it, and as it's been building it, it's been putting in these instrumentation locations where we can get results about a program running. Cool, huh? Well, let's go check the program works. Go to source. Here's a copy of TCPIC. Let's run it. It appears to do exactly the same as before. Let's validate that it can read the file I made, james.pcap. With some arguments that I got from its man page. Yeah, cool. So still working. Oh, it doesn't like the -v0. There we go. That's nicer. So that's yeah, it's looking good. We have a functional program, but it's been instrumented with AFL. We go a little file on it. You can see the details of it. And this is a 64-bit version. This original bug was a 32-bit bug, but you know, we've got this program compiling and building. Let's see what happens in 64-bit world. Of course, again, a very useful use case of foundations, understanding the architectural differences between the two. And when it comes to these more advanced reversing and exploitation cases, some of those understandings of the difference really will accelerate your ability to kind of comprehend how to do these more advanced things. Okay, so time to make this interesting. Now we are going to run AFL fuzz, which is the program that actually does the fuzzing, and it requires a few arguments. AFL fuzz -i in -o out. So that's input directory, output directory. Go figure. Then the program name, which is source tcpic. And then it expects the arguments that it must run the program with each time. We're going to do -r for read the pcap file at. And the at says insert the file here. So each time it generates a new test case, it inserts it to that location. Then we'll do the wrf1v0 that we did before. Okay, so this is our input directory where my data is, my output directory, my copy of the program, and this little trick here to say, keep opening the program and iterating on the file. Hopefully this is all making sense. Again, foundational skills, a bit of bash scripting and syntax, very useful here. Okay. Oh yeah, standard protocol, there we go. AFL telling me that unfortunately my system configuration is wrong, but that's an easy, quick fix with some copy and paste. Here we go. All right, it's working. So notice the red bits already. We have, oh, is this going to work? That's the world's smallest and least impressive zoom. Isn't that shiny? So we can see we have a total number of 6 crashes so far, 6 unique ones, and many, many crashes overall, which is pretty funky. I mean, we've broken this program a lot already, and A, because it's buggy and rubbish, and B, because look at this. Look at the number of executions per second, 920 executions per second. I've done 46,000 already. That's a lot faster than I'd be manually crafting my test cases here. So I'm a big fan of machine learning and automation in this particular case. You can see the methods it's trying. You can read up on how it's doing that, the coverage of the program overall. And you know, now we could leave it here running to try and find lots and lots of bugs. But this is a wonderful example because it's Well, it's so bad, it happens quickly. Of course, with PHP, we were running across 128 cores multiplied by 4 servers for a month, lots and lots of execution time to get to places that other people hadn't been before. So you can make this work across multiple invocations in parallel to scale this up, bit of grid computing, which is mightily fun indeed. All right. So this is going through and generating these crash files and generating these test cases. I'm going to ask it to stop for a minute, and we're going to go to the out directory and have a look at what we generated. Well, in the crashes folder, we have a number of crash files. Now, these are named to tell us a little bit about where they found the bug, the type of rule that was used to kind of cause the crash, but they're actually data. So let's have a look at ID 0000, SIG11's a super catchy name. Actually, let's just move that to an easier to type name like Flibble. There we go. Let's vi Flibble, hex edit mode, and you'll notice Flibble has some similar properties to the file we looked at before. It looks like a PCAP. Remember my point about the 45 as the beginning of the IP header, the 45 there. All right. If you don't believe me, let me read Flibble with TCP dump. Oops. There we go. So it's reading it as a PCAP file, and it's showing me some data from before, but this time it says invalid packet capture length bigger than snap length. It's a very big number indeed, isn't it? That's mighty curious. Now the program hasn't crashed, it's just upset, doesn't like the data. So what's happened is we generated lots and lots and lots and lots and lots of variations of this data, and then caused the program to have a little bit of a meltdown. Let's try it now with tcpic to see what might have happened here. And again, I hope you're all following and I hope you're all having fun. I certainly am. So thank you for coming on this journey with me. I'm really hoping this is going to lead to a good place, and then we can go and break a program. All right. So I'm going to run //source tcpic -r flibble wrf0-v0. Cool. Segmentation fault. All right, the program crashed. So this is interesting. We have a file now, Flibble, that if we open with tcpic, causes the program to break for some reason. This is a bit like if I generated a HTML file and hosted on a web server, and you browsed it with your browser, it would crash. It invokes some part of functionality in the program that causes an issue. Again, we understand from our general foundational theory what a segmentation fault is, and that we've got some kind of memory access violation issue going on here. Something's trying to access something or write something that it shouldn't. But we want to know a little bit more than that. And we want to understand whether this particular file we found is useful to us, whether it can do more than just crash the program. Well, before we start using this file for analysis, we really want to tidy it up. What we want is the simplest version of this file that causes the crash. If you think about it, all this data here is really, it's pesky, it's annoying data. We want lots and lots of data that's clean and easy to read, so that when we're analyzing the bug, we don't have lots of information all over our stack and throughout memory. I mean, from our foundational knowledge, we know what the stack is, we know what the heap is. We may have played with some debuggers a little bit, but it's just harder when you're dealing with more complex data. So let's simplify it. And thankfully, we don't have to do that work ourselves. We can actually, in this case, ask AFL to do the minimization for us. Now, before I run this particular program that's going to magically do this, great question from Charles here. Charles, I'm So happy you're paying attention late this evening. I can tell from the question you've asked. Is AFL used for any program that accepts an input file? Spot on, Charles. It requires an input file, a binary input file. Could be text, could be binary. I mean, text just being binary. However, you can also make a harness. So you can build a program that expects input via some other channel like network, and you can say to AFL, put data here. It's just a dash more complex setup. It's really easy with a file. What it's not good for is if you were, for example, attacking a hardware appliance where you have no physical access to the host. You only get network access. You'd need a different type of approach in that scenario, different type of instrumentation, different type of fuzzing tool. But if you can get access to the binary, or ideally the source code, usually you can coax it into working. It's just really easy in a file input scenario. It's well documented. You can actually have a little read about that online. If you have a search for AFL non-file input, you'll find little walkthroughs through it that you can spend some time trying after this talk. So great question, Charles. Very observant, and hope that helps you. All right, let's do some minimization of our file here. So we're going to say AFL-tmin for minimization of a test case. Input is flibble, output is sweet min. Great name. It needs the command again. So we're going to run // source / tcpic -r, insert file here, -wr -f1 -v0. Looks right. There we go. So look at this. It's done a bunch of character minimization, symbol minimization, block removals. It's simplified it 427.83% through 596 executions. Now, I don't know about you, but rather than opening this file up and manually patching it byte by byte in hex, that was eminently favorable. I just ran a program and used a bit of algorithmic approach here and instrumentation to solve the problem for me. We like. So let's have a look at our corresponding file. Open it in hex mode again and look at it. It's a bunch of 30s, mostly. 30s being an ASCII 0, followed by a terminator, certain length. It's really basic. However, purportedly, this will create the same crash, the same problem that we saw with the other file. So let's see if that's true, shall we? We're going to do that by running the program. Instead of running flipple, we'll run sweetmin. And look at that. We do indeed get a segmentation fault. So our simplified file causes the same bug to be invoked, the segmentation fault. Well, I already have a good idea why. And I have a good idea why because of foundational knowledge again, but then we're going to go prove it in a debugger. Again, I hope you're all having fun, and thanks for sticking with me. I know these talks are long, but I'm having a bit of a blast here. So my theory on why this is crashing is this little value here. When we're learning the foundations of how computers execute, we learn about data types. We learn about integers. We learn about decimals, floats. We learn about signed integers and unsigned integers. Signed integers representing values that are negative and positive. Unsigned representing only those that are positive. Well, the interesting thing is, if you look at how data is laid out, a signed integer uses some of the most significant bits of the kind of value to denote the signing, the negative, which means if you read a signed integer that's negative as unsigned, it is an astronomically huge number. This value here ought to be our fragment offset. Now, those of you who know network packets know those are some pretty weird fragment values. But what you shouldn't be having is a count of fragments that's negative. That should be a positive value. And it's really weird that it's showing up as negative. More than likely, the program trying to handle that negative value is crashing in some subtle and odd way. So let's see if that's the case. We're going to go back to our build of TCP. Clear ourselves out. We'll make sure we still have our in and out directory, which we do. And we're just going to rebuild TCP a little bit here. We're going to change the arguments to make them friendly to debugging. Again, you could do this without doing this step. It just makes it a little bit easier. GGDB, so we're optimizing it for GDB, the debugger, which is nice because it's going to pull in the source code and make it a bit easier to read. That might work. Yeah, looked like it functioned. So my command there was just basically saying, give me a version of this program that's optimized for debugging so I can have a look at what's going on. Let's do what we always do. Let's check the program actually works. Looks like it. Let's check the crash still happens. Sweep min. -WR -F1 -V0. Cool. So crash still happens. We have our debugging friendly version. So we're going to do GDB. By the way, look at that lovely little shell highlight there. Just going to keep talking about how delightful my shell is and how good Vi is until everyone submits to my way of thinking. It's my ultimate master plan. So let's open up TCP. There we go. And now, in this little debugger, we can have a look at the program. We can list functions that are inside this program and look how rich the information is. Now, again, depending on your background, you may not have done much reversing before. You may not have used tools like this, and that's perfectly okay for this demonstration. All this tool is doing is letting us look through the TCP binary as a compiled program and have a look at what the functions are, how it's constructed. We can see these massive memory addresses here, these 48-bit addresses on a 64-bit architecture. But these are yet to be assigned as the program has yet to start. Well, I'm not going to get too clever here. All we're going to do in this debugger is run the program, and we're going to read in the file crashes sweepmin as before. So there we go. It starts the program. We get our -8 as before. We get our segmentation fault. But now we're inside a debugger. We actually get a little bit more detail about what's happening. So what I'm going to do is trigger a backtrace. Here we go. And what a backtrace does is shows us the kind of procedure call chain, the function call chain. It shows us which functions invoked which, one after the other. So we can kind of see where we are in a program. Again, great foundational knowledge to know how programs execute so that we can in turn understand this kind of debugging stuff here and what's going on. So let me step through a high-level version of this and where this bug comes from, and then we'll back out to the patch to see why it occurs. So we were in the main function where most programs start. We went into pcap loop, presumably something that iterates through the pcap, pulling out packet by packet. We went into a function named ? That's because we ended up inside a library called libpcap. This is a shared object. It's provided by the operating system here and the lib directory. And it's stripped. So we don't know the name of the function. We're in some functionality at that location. Then we were inside got packet. Well, I guess that got a packet. As it's looping, it grabs the packet and calls get packet. There's some arguments here. HDR, packet, useless, strange variable name. I'm guessing this is the header. This is the packet. It's probably where in memory the particular packet is at loop.c. So we can see here the program, the code in loop.c is responsible for this bit of functionality. We've got established packet after verify.c. Well, I'm guessing verify does structural integrity checks. Is this data expected? Then it does established packet in order to kind of validate it and put it into its own structure for analysis. So, I mean, even without doing much code reading here, just a little bit of our foundational expertise, we can start to piece together a bit of what's happening with this program. And yeah, this is getting moderately advanced now. So hopefully you've all had your evening coffees. Well, now we start to get towards the source of the crash. Here we have at fragments.c, remembering fragments is what I said I thought was going to be the problem because of this fragment size here. It's got some arguments, wlen, data off, payload, repeats a number of times, incomplete sequence, payload length equals -8. So we're in fragments.c and we've got a payload variable called -8 here. So this is a fragment size of -8, we could guess. Well, go figure. The next thing that happens is sysdeps x86-64 multi-arch memmove vec aligned ERMS, which is easy for me to say. It's a mem copy. It's trying to move data using these arguments. But notice here, the payload length is -8. It's trying to move this packet, but the length value being provided to memcopy is massive. Look at the size of that monster. And that's because this -8 is being interpreted as a positive sign value. And the negative value here, we know from our foundational knowledge, the signing uses the most significant bits. So we end up with a huge, huge, huge number. You can go Google unsigned, signed, converter, 64-bit and paste the number in to see that this works if you'd like. So memcopy is trying to copy memory. And of course, the segmentation fault is occurring. It's trying to read from and then copy an astronomical amount of memory to somewhere else. It's read violating or write violating. I mean, it's just never going to work. What's interesting here is user supplied data from a file is causing a copy. Now, hypothetically, this bug, as opposed to just crashing the program, might be useful if you could trick it into writing data or copying and overwriting data into just the right place. Maybe we could provide a packet that contains a value that overwrites a security token at a predictable location. Then when someone tried to open this PCAP file, it would in turn cause the program to crash and enable us to overwrite that value and get control. Sound far-fetched? It actually happened with Wireshark. I actually got to do it in a red team exercise a few years back. This was really cool. This was a bug that first turned up with a version of Wireshark on Windows XP. And this particular blue team were running a copy of Wireshark on their Windows 7 system, as it was, we were targeting. And we took the exploit from Windows XP for that Wireshark, ported it to Windows 7 with a few careful changes. And we were actually able to trick Wireshark from the blue team into reading the packets, getting exploited, and giving us, the red team, control over the blue team systems, which was so much fun in the red on blue exercise. You could imagine the chaos that ensued when you're able to see the defenders as you're running through the red on blue exercise was really cool. Now, an older bug, but it shows you practical. Now, let me show you where this bug comes from and the horror of how they fixed it. And then we're going to jump on to using these foundational skills on a couple of kind of exploitable things here. Again, I hope you're all still having fun with me. I know this is getting a bit more gnarly as we go. And remember, the questions are there. If you have any queries about how this stuff's working, anything you'd like me to cover more than happy to do it. So let me jump out of the debugger. Now we can see why this crash occurs. And let's go back to that patch directory. If I can remember how to use a computer, I will do much better. Here is our nice old patch file, nice ancient bug I picked. And remember, the patch file, using our foundational skills of a bit of programming and understanding syntax, shows us what's been taken in and out. And I always love, it's really reassuring when you read code to see something like a comment that says, fix me, sucks. Probably not a good sign. Down here, a temporary fix for this bug. The temporary fix is still there, by the way. And it says, if the buffer length is less than 0, the buffer length is 0. So this is obviously targeting the case where we have a -8. And if that value ends up being less than 0, it just overwrites it with a 0. So rather than actually fixing the code to be strict on types, it just adds an if condition that patches the data. Again, a bit of programming knowledge might lead us to understand this might be exploitable in the future. If this has been so tactically done, is there another value that can be controlled this way? Is it possible instead to supply a very large value, because it's only checking negative ones? Can we provide a very large value that's useful to us in an overwrite way that doesn't fall victim to this check? Again, our foundational skills can move us towards being able to do more advanced bug work here by reading a file like this. Okay, so that's some automated bug hunting with AFL. And of course, we've got lots of other crashes to look at there and to explore. You could take these techniques and try it on some programs of your own, maybe programs you have in your own business, and then work through, seeing how those crashes actually occur. But I want to change pace a little bit here as we're in hour 2, and show you a little bit of actually kind of debugging and breaking stuff. And I want to start with something a little more simple, and then something more advanced, but something that can be solved with a shell script. And this is always beautiful. We do a lot of CTS with really tough challenges, and people spend ages writing complex programs to solve them. Just kind of go, ah, as they watch us defeat it with, something like bash. So let me jump over to this second example now. And again, if you have any questions about the first example, what I'm doing, remember the Q&A is there. Don't be shy. Well, I was going to say there aren't any stupid questions. Technically, that's not true. But, there's a lot of very good questions you can ask, and you can be very confused and ask anything you want to unashamedly, anonymously if you'd like to. But no stupid questions. It's slightly trite. Okay, so let's have a look at this really contrived, awful program. And I'm going to show you the source code for it as another example of where some foundational programming can be useful. And then we're going to do some basic exploitation of it. And then we're going to step up to a hard one. So this is the code, this one. It's really bad. This is some really awful C. I'm so sorry. And it's an example I've used before as a basic example of a kind of classic programming error. But it's usefully simple in this quick walkthrough here. what we do first is declare a buffer. And this buffer is a char array. So it has a type of bytes and a size of 20. So that's a buffer that can be used for user input data or whatever else the program wants. Right next to it, we have an integer set to authenticated equals 0. So an initial value of 0 has been set. We print out, please enter the password. We get a copy of the password using the gets function. Pro tip, this is an awful function. It doesn't support bounds checking. It's got all kinds of awful security issues with it. There are lots of other banned functions, by the way, and unfortunately they still turn up in modern programs, despite the fact they've been banned for years. As you'll see, when we compile this program, the computer will scream and shout about it, but we'll respectfully ignore it and run the program anyway, as happens in a lot of programs. Now we have a password check. If strcomp, the buffer, equals password 1337, print access denied, else access granted, set authenticated to 1. So we get the password right, authenticated becomes 1. It becomes true. Then we wrote below, if authenticated, and this just basically means if not 0, if it's true, then print super secure code executed, set UID to 0, and print the contents of the etc shadow file. And this could be any privileged operation. I did this just because it looked cool. The point is, if the password authentication is passed, trigger this code branch with this if. Now, any of you who've been kind of studying the fundamentals and done a bit of programming will see several things in here that make you cringe, such as gets, which allows inputting more data than you ought to be able to store. There's actually this mechanism of authenticated equals 1 and a check below, this synchronous logic is not necessarily the most secure thing, but also actually pretty unreadable and confusing. And yet patterns like this exist in production programs all the time. People grab quick bits of code from Stack Overflow, paste them in and go, yeah, looks like it's working. I've tested so many applications where it looks like the data is encrypted, but actually none of the setup was ever done to make the encryption secure. So let's go compile a copy of this program quickly, take a quick eyeball at it in a debugger and break it, and then we can loop round to a more interesting little CTF challenge here to round out. And remember, lots of Q&A time at the end. So if you have questions, make sure you're dropping them in there now so I can answer as many of them as possible. I've got a copy of this program compiled called Keynote 1, and it's been built with debugging so that it's easy to see what's going on. You'll recognize the functionality. I run it, it says access denied. Now I've seen the source code, so I know the password, but we're going to ignore that fact because that doesn't make this particularly interesting. So let's say we had this program and we wanted to exploit it here. Well, we could open it up with GDB like we did before. We could look at the functions in it and see things like gets that we know is very concerning. We can have a look at the main function and see this, well, rather less than readable screen of text. Now, again, some foundational understanding here really helps us. We start to know some of the lower level operations of what a computer's doing when it's storing information. It makes it easier to kind of follow this stuff here. But I'm going to show you a great cheat that can make our lives a little bit easier. Here's a call to gets, which is where we're presumably going to get our user input. But we have the code to this program, which makes learning to reverse it and debug it a lot easier. We can do that with the list command. So for example, I could say L line 1 to 40, and it prints out the code that it was used to build the program. For example, now I could see if authenticated. Well, maybe some of you on here haven't done a lot of reversing before, and you can't spot if authenticated in here. I mean, it's not very obvious, honestly. It's actually in here somewhere. It's pretty tough, but you can cheat by using this little trick I've shown you, 1 to 40. I can say if authenticated is line 23. So I can say, debugger, please break on line 23. And it says, I would love to do that for you. So let's run the program and put in a password of just a bunch of A's. We do that because it's easy to spot. And it hits the breakpoint. If I now do dysas main and scroll down, you'll see it actually highlights for me where this is in the assembly. That's a huge deal. Think about that for a moment. You could build simple programs in C, compile them, open them with a debugger, and use this trick to see what the code looks like, and in turn, figure out, you know, a little bit of assembly and how to start doing some debugging. So a little bit of programming can help you with this advanced reversing skill and practicing over time. All right, a couple of questions here, and then we'll jump on with this bit of exploitation. So what have we got here? 5.6 video. I know they teased it. I'm sure they're going to publish it soon because I know it's been made. Don't be surprised when it's published if it's got the Rick Astley trollolol background noise though. Are those get push call access to the lowest level atomic operations a Keynote program is executing? Wonderful question, Mark. Somewhat. There are lower level operations here. So some of these, like, you know, an add or a load effective address, a move, are very much the lower level atomic operations that a computer uses to execute code. Simple arithmetic like IMUL. This is a mnemonic representation of machine code. So believe it or not, what you're looking at is the very readable version of the truly lower level machine code. But it is actually the representation of the most atomic operations, like a test or an add. Some of these are a little above that, like a call to strcomp is going off to a function that is in itself constructed of all these atomic lower level operations, like moving data around. So you're seeing it at its most atomic level in an easy to read format, but the functions might combine together those atomic operations to do something bigger. And I'd like to take a moment just amidst the foundations to think about how crazy that is. You're calling a function that does a string comparison, gets user input, a function that prints a graphic to the screen, and thousands of times per second, simple arithmetic or memory move operations are used, thousands and thousands and thousands of times per second, even on a single core system. Those simple atomic operations are used to do everything you see in front of you in your computer. The second hand moving in the clock, the network packets being processed, the video being rendered. We're looking at just a sheer volume of information processing of these atomic operations that is mind-bogglingly awesome. So Mark, you know, kind of a yes with a couple of exceptions there. And thank you for highlighting something as well that is really a miracle of modern engineering. I also want you to take a moment after this presentation to think about how each of those is fluctuations in voltage on a chip, a piece of silicon, little gates changing between ones and zeros, and the sheer velocity of those changes to represent these atomic operations in logic, more foundational knowledge here, logic and axiomatic operations, and the subtleties of voltage in a tiny piece of silicon that physically occur to represent each of these changes thousands and thousands and thousands and thousands of times per second. It is awesome and probably makes you want to go listen to the Feynman lectures or something else like that. If you don't know what I'm talking about, you should go listen to them because they're absolutely fascinating, and the physics is almost as good as the computing here. That's where the foundations and lower level understanding can become beautiful and help you understand these really quite advanced cybersecurity skills like like reversing. Oh, yeah, there you go. Mark says, this is exactly why I asked. Not having any reverse engineering experience and not being a programmer, this is the first time I've seen through the microscope, and coupled with your fantastic explanation really helps understanding what's happening at a physical level. My pleasure, Mark. And hopefully I have sent you off to several weekends of a rabbit hole of Wikipedia, of architectural understanding and the foundations underneath. It really is beautiful and amazing. And it really does build a bench of foundational skills that helps you learn this more advanced stuff quicker. So, thank you so much. I have a challenge here from Chandra as well on a keynote on quantum cryptography. I would love to do that, and I will make a note to our SANS organizers here for a follow-up. That's a pretty fascinating intersection of maths, physics, and kind of latest computing theory, even at a high level. The kind of application of the difficulty of quantum observation to quantum key distribution is pretty remarkable. So challenge accepted. We'll get that on the calendar somewhere. All right. GME to moon when? Tomorrow. Definitely tomorrow. All right. Let me run on through a little bit more of the demo here as well. Thank you for all the questions and for continuing to go on this journey with me here. So this is pretty neat. We were able to use the debugger and code to figure out the little lower level instruction that's actually used to check if authentication equals true. Well, here's a cool thing. We can actually look at this location in memory if we want to. What it's saying is, I'd like to do a comparison of 0 against a location in memory that is EBP, that's a register. At that location, I'd like to offset by 0xC. Ooh, lots to process there. Short version, it's going to a location stored in this special register. Foundational knowledge again, how CPUs work, what a register is. At that location, if we offset by 0xC in hexadecimal, more foundational knowledge, we should find a value that's been stored by the program. And depending on whether it equals 0 or not, it will jump and execute different code. That's authenticated. If it's not 0, go do stuff. If it's 0, don't do that stuff. So this is the assembly version, the compiler built of the C code that we saw. And again, if you don't see it right now, don't panic. This is tougher stuff. It takes time to learn. Several people here will be in classes learning it this week, like looking at some wonderful skills in 610, for example, and reversing. So let's have a look at this memory location just for fun here. I'm just going to say grab the hex value from EBP minus 0xC. And I mean, nothing there. Okay, so I guess that's somewhat to be expected. Let's continue running the program and executes as normal. So we have our zeros. Well, what if we could overwrite enough data to cause this value here of these zeros to contain something other than 0? Let's go look at our program again and see if we can trick it into doing this. So here's the code, basic.c. Note up the top here, we have a value of buffer 20, followed by int authenticated. Remember, with some basic programming knowledge, this is comparatively a high-level language. Oh, it's so far from the assembly and low-level instructions we were just looking at, even though it's nothing like Python or truly higher-level languages. So this is going to be put into memory and checked. But the compiler's probably going to do some things to optimize it. So yeah, Mark, you're going exactly to the right place. And it's going to be a small variation on a buffer overflow here. Mark's saying overflow the buffer right to a memory address. We're going to overflow the buffer and trample authenticated. Because if we can write a single bit into that authenticated value with an overflow, it will be greater than 0, which will make it true, which will mean if authenticated will pass. and it will run the code that we want to. So let's do this. We're going to do Python-C print a times 20 to start, just to get some A's. And we're going to pipe it into Keynote 1. We get access denied. And that's expected because we've written 21 bytes of data, actually, 20 A's followed by a return. So that's 21 bytes. So we could try 24. We have got here a lovely, delightful execution of the super secure code. So somewhere after that buffer there, we've actually succeeded in overwriting int authenticated. And when it got to that line in the program, it ran the check, the comp L 0x0 against -0xC EBP, and at that location, gets had written some data that it shouldn't have. Now, I don't know whether 2 A's made it in there, 1 A, part of an A, it doesn't matter. All that's required is it's not 0, and now we have a copy of the etc shadow file. And make sure you don't rewatch this video and crack my password hash. That would be a very unreasonable thing to do. So isn't that neat? We have, the basis here of a very simple exploit. And of course, we could now try each of the values to figure out exactly what size triggers the overflow. And here, it's pretty neat. The way the compiler's built the program, it's 1 byte right after the 20. We declared a buffer of 20, and off we go. Of course, we can see that in our debugged program as well, trying this piece by piece and watching that area of data we identified until it's a non-zero value. So this is, equivalent to your point here, Mark, to overwriting a security token. Now, there's lots of things that the developer could have done to make this equally exploitable, but look harder. For example, int authenticated could have been set to the text string no. And then below, it could have checked that text string equals yes. Well, in that case, we'd have to, write something like or the expected data. And we'd have to figure out the exact right positioning to get it into the right location. Perhaps there's a scenario where there's a user ID that's set to 1337 and we want it to be 0 and it's at something like an offset of 24. And we could overwrite it with zeros once again. This can actually be tricky in of itself dealing with nulls, but that's a lecture for another day here that again relies on some basics of string processing and programming that are well worth learning as foundations. So hopefully you're starting to build this picture of a bit of understanding of memory and the atomics can unlock these more advanced exploitation and reversing skills here. We've broken this slightly contrived program and seen how this code is a little bit poor. If you are interested in how you could fix it, you could do something like changing this fgets instead to this gets to an fgets and saying something like buffer size of 20 from standard in so that it can't go beyond the boundaries. There are lots of other ways to make this robust. Of course, what does often happen is something like this, where it's set to 20, some developer comes along and sets this to 16, and you have a secure function used insecurely because of a code change, right? We're still allowed to enter 20 bytes, and it will write 20, even though its destination is only 16. So code changes over time can introduce more subtle bugs. Again, value of foundations in low-level memory understanding and programming. All right, I would love to show you one more little example here for fun, using some bash and a bit of a CTF challenge. But you are welcome to vote with your feet if you're bored now and I've killed you already. Feel free to run away and do something else. But I see lots of you are still here, so let's turn it up a notch once more and do one more example here in our remaining time. And thank you for hanging out with me for so long as well. I know it's a mighty long Zoom session when we've all had a year of Zoom. Where's my target program here? Keynote 2. Brilliant. So this Keynote 2 program is it's pretty terrible. It is one that I built for a Catch the Flag challenge. The code is complex-ish. However, for the CTF challenge in question, you don't get the code. But it does show the value potentially of things like programming again, if you want to help, training your colleagues and challenging them. Programming and understanding memory can be a useful skill once again. So let's just run this program and put in some data. Nothing interesting happens. Well, let's take the prior approach. And in this particular case, we're not going to use a debugger because this CTF challenge was running on a remote network server where you couldn't actually monitor it. So let's just send 1,000 A's like that. Love some A's. Xerox 41s are the best. And we get a crash. And it actually returns it back over the network from an error handler. It says segmentation fault EIP 41414141. Test called get flag at this location. Well, that's cool. We know where the get flag function is. And if you've ever done a CTF, you'll know that get flag is very interesting to us indeed. That's the one that's going to give us the answer and give us the points. Small problem. If I run it a few times, the address keeps changing. Not awesome. So the problem here is it's running a mitigation called address space layout randomization. Foundational knowledge, understanding how computers have built defenses and manipulate memory to make our lives harder. In theory, what we want to do is provide some input that overwrites a value that gives us control of execution and point it to get flag. But we have no idea how much data that is to write to it. And we have no idea how to get to this address that keeps moving. And we have to solve it without a debugger. This is feeling pretty tough. However, we're going to use some wonderfully foundational skills and some dirty hacking here to solve this problem. It's going to be fun. So, first job, find out when the program crashes. We're going to use a bash for loop. For I in 80. Oh, I need to use the right program name. There we go. So this is just going to say, go through and set I to 0 to 1 to 3 to 4 to 5 to 6, 7, 8, 9, 10. I didn't want to do 1,000. It would take a really long time. Print out I is at I, and then run Python A times I and feed it into the Keynote program. It's so horrible. No advanced hacking here. We're using a bash script in effect to figure out an offset. Notice here I did flip the quotes on Python. That's because if you do it the other way around, this $I doesn't get interpreted by the shell, and it literally sends $I. So I actually use the quotes the other way around, where speech quotes say, go in here and substitute these values. Great foundational skill again. I had a penny for every time I said that. So let's run it. And you can see at some point it starts throwing out the error, and it didn't earlier on. So again, this is treating this like a network service, no debugger. We can see at 74, so between 74 and 73, we start getting the issue. So now we know from our log entries here, somewhere around 74, 73, we have a crash condition. Isn't that beautifully dirty and simple versus, taking some complex fuzzing tool or writing something? Let's test that. So let's just do Python a print a times 73 and feed it into Keynote 2. Go to 74 and it crashes. So now we know a size that overwrites the data. But it's a bit weird. We got a 0A, which is a line terminator, and we've got a 41, which is an A. And that's weird because, you know, you'd expect the 41 to be here and the line terminator to be after it, which is really bizarre. If I make it 75, I've got an A, a line terminator, then an A, which is weird because these things should be running in order. I mean, look at that. That's just kind of strange. Now I've forced my line terminator over here, and the 41's overwritten the 0. So it seems like there's some byte that we can't control that contains an A, but we're supplying A's. We're going to solve that problem in a moment. Let's remember that and go back to our 73 here. Well, we know the get flag is at this memory address, and every time we run it, we're getting a new address. But there aren't infinite combinations. In fact, if you look at the prior set, you'll see the BD0 isn't really changing. The most significant bits aren't shifting. It's the bits afterwards that are changing. So it doesn't look like it's particularly high entropy. This is not, you know, Vegas. We're not playing blackjack here, and we get as many goes as we like. So from our foundational understandings, understanding that randomness is something where we want high quality randomness, and maybe we don't have it, this might be breakable. So all we're going to do here is put in our memory address of the get flag function on the last run, \x66 \x d0 \x d0 \x0b. So all I've done is write that in little endian, computer architecture and low-level understanding again. 0bd d0 d066. So let's run it. And you can see we nearly got this right. What we have here is a 41 and then a BD, which came from, our BD came from, I guess, that bit. Then we have our D0, D0, but we kind of lost some data here. Something a bit funky is going on. Now, what you're seeing is us just iterating and repairing the attack because we don't have the ability to debug it and actually figure it out or look at the code. So let's play with this a little bit. And let's remember that 73 A's cause an interesting crash. So I'm going to do Python-C. I'm going to say print A, B, C, D, E, F, G, H, I, J plus Z, Z, whichever pronunciation it is in your particular vernacular, times 100, like that. And I'm going to feed that into my program. Well, this is very interesting now. We can start to see what's going on. We have these 5A, 5A, 5As. If you go look at the hex to ASCII equivalent, you'll see that is a Z. And that Z is what we're seeing here, overwriting the data, as we'd expect from our attack above. But interestingly, right at the beginning, we have a 43. Well, we know, again, foundational, ASCII, that A is 0x41, therefore a B is 0x42, therefore a C is 0x43, which is weird because it means this byte is leaking into the address. So we're overwriting, but the data from earlier is trampling it. And this is a thing that happens in more complex programs and more complex exploits. There's getting some hard stuff to solve now. but we're just using logical data and little tests, the mindset of a developer building test cases to solve this. So if we know that particular byte causes a problem, let's go back to our exploit now and just patch it up a bit. All I'm going to do is I'm going to make this 70 A's, and on the front of it, I'm going to put the flag value that I wanted, the 0B. So I'm going to put \x0b, 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 where the third one is the one that should count. Okay, so I run it. Yeah, it's overwriting itself, Chandra, exactly. What's probably happening is we're overwriting data in the program, some other functionalities coming along, using data from earlier and copying it to that location. That happens in non-contrived context because programs don't just do one simple thing. They have lots of functionality occurring, and we have to compensate for it. All right, we are starting to get somewhere here. Let's have a look. Okay, so we have our 0B, our 0B, our A's, 71. And it doesn't like zero A, 0B, 66, D0, D0. Let's put in a CA here so I can see what it does. All right, we're close. We've got 0B, 0B, 0B. We've got our A's times 71. I think our B's might be causing us a problem. 60, 60, 0, CA, 0B. Yeah, I think what's happening is I'm trampling it with the 0, the 0B at the beginning. I think it doesn't like my my 0B value versus something else. So we've got a little bit of a data alignment issue. Let me just put in a little bit more here. Yeah, I think that's what's going on. So back to the data, I can see the 43. Direct B. There it is. Missing a plus. There you go. I did that just to make sure you're all paying attention at the end there. I was missing my plus in my syntax, so I was just overwriting myself before I actually supplied the data. Yay! Python syntax, really important. Programming, foundational skill. Okay, so now we can see my 0xb CAD066. All right, let me have a last little look here. I'm going to take the last value, which was BD0D D06D. So I'm going to say I want 0xb, which is this one, and then I'm going to say D0 D06D. So it matches this prior address. Okay, I run it, and it's looking pretty good. The problem is that it's no longer at that address. So to wrap this up, let's do this a really gross way. It's going to be super fun. We're going to do while one do run this again, and we're going to grep -v segmentation and we're going to grep -v, foundational skills, Linux scripting, backtrace. So we're going to get rid of these 2 lines. Oh, let's grep -v, welcome. In other words, remove the standard output of the program. And now we're going to run it a bunch of times. And look at that. If I keep running it again and again and again and again, removing all the other outputs, every once in a while, the program recycles the address that I first copied, and it successfully calls the function, and I get the answer here. Again, a bit of bash scripting being used to try lots and lots and lots of times. And we're actually, bypassing a real security control of modern operating systems here with a bit of programming syntax, a bit of for loops, a bit of patience, and a bit of architectural understanding. Isn't that cool? Like looking at how the leak byte drops in, looking at which bit to overwrite, just a little bit of understanding of how programs execute, and you can get to really quite an advanced capability here. So I'm hoping that you enjoyed that little walkthrough. I can see Chandra says, literally on the edge of my seat, probably screaming, why didn't you add the plus? Watching me make a mistake in my my 2 hours of live demos here. So let me start to wrap up here. I want to share just one more little thing with you. My pleasure, Mark. Mark says, thanks for pulling back the veil. Really tough to make this content work for such a diverse audience of varying ability levels. If you didn't get it all, don't worry. Hopefully you picked up a few pieces of it, and that idea of how understanding execution can supercharge your security learning. The same applies to other areas as well of these. It can apply to networking just as easily, understanding how packets are processed. Look at how that was useful in our very first demo in bug hunting. Building this broad base of skills that you can call on, breaking down the silos and the boundaries as a security practitioner, just supercharges your ability to consume all of this knowledge in a really powerful way. So last couple of notes here, and then I'll pick up any final questions that are coming in. Like to take a moment to recognize the SANS.org/free page. If you haven't run across this, it's pretty awesome. It's a collection of hundreds of tools produced by our faculty and alumni. Amazing tools that are incredibly useful for cybersecurity practice. I want to give a huge thanks to our alumni and our instructors, the world-class practitioners that build this stuff. Go have a look at their work, see if you can find a way to contribute. It's pretty awesome. You'll also find amazing posters, amazing blogs, videos, and articles where you can learn more, like this talk. You can also have a look at some of the summits and free learning resources. You can find kind of access to CTFs and community challenges to practice challenges just like this as well. So a reminder, SANS does an awful lot for the community, and do swing by there and have a look at those resources and share them around with your colleagues as well. I believe there's also a recording of this talk that is made available and can be found as well. So feel free to share it with someone who you think might be useful. I mentioned the SANS Foundations project, as Chandra mentions in the chat, living up to that earlier comment where I nearly threw my computer off the desk. You can find more information on sans.org/sans-foundations or sans-foundations.com. This is ultimately a course that's designed to teach the foundations. Some of you here might be beyond that and just enjoyed watching my demonstrations, and you're off into more advanced courses, and that's wonderful. I really hope that my message of the importance of the foundations and how some of us learned these fundamentals whilst configuring our video games and how technology's changed resonated. And I hope you can help me spread the word of the importance of breaking down the black box nature of technology and being able to understand the atomic execution and why that's so powerful to us in learning security skills. If you have newcomers to the industry and folks that are looking for a way to get started, I'm pretty excited about this this project as a way to fast track their subsequent security learning. and you can find more information there. With that, I'm going to leave the talk here, and great to see so many of you. Wow, you stayed up till 1:30 in the morning. Thank you, anonymous attendee. Feels weird to say that, but an absolute pleasure. I really enjoyed myself. And if you were confused about any aspects of the talk, remember you can skip back over the recording, watch it again. Of course, lots of great resources online on sans.org/free and other sites walking through these types of walkthroughs. A huge thanks again to the authors of the tools, like the author of AFL. Do go check out their site, read how this stuff works. As I mentioned to Mark, there is a lot of extra homework to be done in reading up on these concepts. This is not a boring area of technology in which to study. Do take some time to walk through the challenges, building simple programs, building them for debugging, looking at compiled code versus source code. A little bit of time investment here will go a long way in all of your future studies. Thank you so much. I believe you'll get an evaluation on the session. Let me know if I can do anything better. You loved it, you hated it, or otherwise. And really appreciate you all hanging out with me for so long this fine evening. With that, we'll bring the session to a close. Have a wonderful week with the various classes and your continued learning with SANS. Thanks for being here, and good luck mastering the foundations on their way to advanced cybersecurity skills. Catch you all later, everyone. Have a great day. Cheerio.